welcome very, very much to Conversations, where I'm pleased to welcome to the program Dr. Michio Kaku. And Dr. Kaku is a professor of theoretical physics here at the City University of New York, and he is a pioneer in the very, very interesting theory of superstring theory and understanding physics. He has written, I might like to show right here at the outset while we're getting started, on what could be an extended conversation into physics and the excitement of it, an incredibly interesting book called Hyperspace, we'll show you right now, that's just out now in the book stands in the spring and summer of 1994. An extremely interesting read, as it were, and it's really a great pleasure to welcome, and it's a great pleasure to welcome to the program Michio Kaku. And Michio, welcome very, very much to Conversation.
Thanks, Harold. It's a real pleasure to be here.
Well, it's my pleasure to welcome you, and I wonder if maybe you could. There's a great deal to talk about. The book is very comprehensive and is written specifically in mind, even though physics has a great deal to do with mathematical formula and mathematical thinking. But this is a book written to try and give an understanding that can be grasped by the layman of the excitement and the developments of physics. It's written in a way that it makes it very accessible to people. Is it difficult to take these complex subjects of physics and right on the cutting edge of physics and make it applicable to the layman? Or do you think some of these most complex ideas of the universe and the theory of everything and some of these things you talk about are concepts that can be made accessible to a wide audience without losing the specialized integrity that is necessary for advancing the field? I just wonder, as a general question, I thank you for the book, but I wonder in general, can some of these very complex ideas, which we do want to talk about, be made available to the general society so that we can have an understanding, as physicists do, of what makes this universe tick, how it got started, and what's going on?
I think so.
All right.
In other words, everyone thinks about space and time, and we see Star Trek, and we see Star Wars, and the Terminator, and we have questions about the universe. That is time travel possible? Can I meet my parents before I was born? Is it possible that there's intelligent life out there that has looking glasses that we can wormhole their way through distant sectors of the galaxy? These are all props of science fiction. However, what the public doesn't realize is that these concepts are also rooted in the most advanced versions of theoretical physics. And these concepts are accessible to children. These concepts are understandable to children. It's only adults that have a hard time visualizing hyperspace and these things, right?
Yeah, right.
Now, the concept, by the way, of looking glass universes was actually introduced by a mathematician who wrote a children's book. He knew that adults would have a hard time grasping the fact that a looking glass could join two universes together. So he wrote it as a children's book, and he called it Alice in Wonderland.
All right.
And Through the Looking Glass.
Yes.
It was Charles Dodgson, a professional mathematician at Oxford University, who said, "This concept is so beautiful, so simple, I shall make it for children." But he was a professional mathematician, writing as Lewis Carroll.
Yes, right, right. And so it was available that way. And he was reflecting things that were developing and understandings that were developing that were very, very complex about understanding the universe. And those complexities and those developments have had a unique history of their own. And I wonder, maybe we could go through it. Maybe we could begin at the beginning. What are we talking about? We go back to 5th century Greece. We go back to the beginning of Euclid geometry. We go back to the beginning of physics. Maybe you could give us a primer of where it is and then bring it up to the contemporary moment. Some of those who were precursors or those that Einstein depended upon, or into a modern phase. Maybe you could give us a primer background of the historical development of physics as we understand it.
Yeah, I'd be glad to, because actually when I was writing this book, I had that very same question in mind. I wrote this book when I was a visiting professor at the Institute for Advanced Study at Princeton.
Yes. And
I wrote this book on the 3rd floor of Fold Hall, directly above Einstein's office.
Wow.
And late at night, when I was on the word processor, I could swear I heard footprints walking down to the library, and it must have been the ghost of Albert Einstein.
Maybe in slippers.
Right.
Yeah, right.
And if you take a look at this long-term perspective, as you pointed out, right, it was Euclid over 2,000 years ago who told us that the world is flat like a tabletop.
Yeah, right.
That we have circles and squares and only 3 dimensions, and that you have length, width, and height.
Right.
But there's just no such thing as a fourth dimension you can place on that.
Yeah, that's like, yeah, right, okay, as that would be the common sense understanding of the way the world is.
That's right.
Yeah,
and if you want to meet someone for lunch in Manhattan, you say,
Yeah.
meet me at the corner of 5th Avenue and 42nd Street.
Right.
On the 20th floor.
There you
okay?
got it, right.
So 3 coordinates, 5th Avenue, 42nd Street, 20th floor, at noon. 4 numbers.
That's 4. That brings in time.
Time.
Right? Yeah.
Gives you the exact location of your lunch date.
Yeah.
And now we physicists are beginning to realize that that conception that came to us from Euclid 2,000 years ago is about to fall because of perhaps the greatest revolution in the last 10 years in theoretical physics, the theory of everything.
Yeah.
That perhaps light, gravity, the nuclear force that makes the stars shine and generates the energy of hydrogen bombs, perhaps that could be explained if you add higher dimensions. Remember, this is no longer Twilight Zone we're talking about. We're now talking about solid physics, whereby physicists are believing that perhaps what mystics used to call the fourth dimension is really the missing link to understanding light. Now let me explain. When I was growing up in San Francisco, there was a Japanese tea garden.
Yes.
And I used to spend just hours at the edge of this tea garden looking at the carp swimming just below the lily pads.
Yes.
And I was a kid. I didn't know anything. I said to myself,
Well, you may have known more than you knew, but I mean, you thought, but anyway, go ahead. Yeah, kids know a lot, but go ahead. Yeah.
but I said to myself, what happens if I were a carp?
Right.
And I was living underneath the lily pads.
Right.
What would my universe look like?
Yeah.
And I said to myself, well, if I was a carp scientist,
Yes.
I would say to myself, the universe is flat. It is two-dimensional, and there's nothing called up. There's nothing up. The universe is shallow. Everybody knows that, and what you cannot measure does not exist. Therefore, the universe must be flat, must be shallow, and they spend their whole time in this universe. And there he was, just a few inches away from this carp, wondering, what would happen if one day I reached in and grabbed one of these carp and lifted them up into the third dimension?
Yes.
All of a sudden, the scientist would say, oh my gosh. They would see lights that are beyond their comprehension.
Right.
They would see people that could move without fins. That is a new law of physics.
That's right.
Movement without fins.
Right.
And they would begin to realize, my God, there is a third dimension. There's a new dimension of space beyond that of the pond. Now today, we physicists believe, not all, because this is an extremely difficult theory to test, but hundreds of physicists believe that we live in a 10-dimensional universe.
All right. Now that's getting into what the title of your book is, hyperspace.
That's right.
This is a hyperspace, a 10-dimensional universe, and but it's been a long row. It's been a long, hard row, as they
That's
say,
right.
to get to this point of development of understanding physics as a discipline and
That's
so
right.
forth. And there's been a great deal. It's been development of quantum mechanics. There's been development of Einstein's theory. There's been people who were precursor to him. That's all part of the story that led to it, made it possible to this. And there's still debates going on between
That's right.
physicists about what it is that makes up the universe.
That's
But in terms of the modern experience, the developments that Einstein was able to come up with and the people who he was dependent upon, there was a mathematician, you go into great detail, or go into detail, but in a way that's interesting to the layman, a Riemann, Riemann, a German
Riemann, right.
Riemann, a
George
German
Riemann.
mathematician. You said also that the guide that Einstein followed, Ernst Mach, a mathematician, a German mathematician.
right.
So this development of the mathematics and the developments of the understandings has been a long row within the modern experience. Within the last 100 years or so, things have been developing as well. And that story is part of what you have in here necessarily for us to understand these broader developments.
Right, right. And in fact, in this
Maybe you
book...
could go over some of that with
Sure.
us in a primer way again.
Right. Yeah, in this book, I tried to summarize the two main currents that have been at the forefront of physics. That is, the theory of gravity, the theory of Einstein and curved space. Also the quantum theory, the theory of particles, the theory of atoms and quarks and molecules. And the nature seems to have two hands. The left hand talks about space, black holes and big bangs and galaxies. And the other hand deals with atoms and neutrons and protons and quarks. And these two hands don't talk to each other.
Particle physics.
Particle physics does not talk to general relativity of Einstein. And it's as if nature had two brains and two arms. Can you imagine walking with two hands and two arms that didn't communicate with each other?
Right.
We cannot believe that nature could be that complicated and silly. that it would have two beautiful formalisms, the formalism of the quantum, of the atom, of the quarks, the neutrons, protons, and X-rays, and whatever, and the formalisms of big bangs and beautiful curved manifolds. That's why we want to merge these two together into one unified theory. The glue was missing, though. We didn't have the glue to put these things together.
Well, the knowledge is growing all the time in the mathematics and the things available to us. The knowledge base is available to us. And one of the things that's coming now in such, the knowledge is coming at such speed and such almost exponential speed. We were talking before off camera about that. The knowledge is coming, but we had to build this up over a period of time. Was Max Planck involved in terms of the quantum mechanics theory or the quantum's understanding?
Right.
Was he involved? And what were and where did Riemann fit in? And what was the development and where did Ernst Mach fit in terms of providing Albert Einstein with some of the guiding principles that he used or utilized in order to come to theory of relativity and some of the basic grounding principles of modern physics?
Right. Think of a sheet of paper, for example, right? This is the world of Euclid, flat, uninteresting, the world of triangles that we had to learn when we were in elementary school. What Riemann said is take this sheet of paper and wrinkle it, okay? Unfold this, and then have an ant walk on this crumpled sheet of paper.
Yeah.
As the ant walked on this crumpled sheet of paper, the ant would say, there's a force.
Yes.
There's a force driving me every which way.
Much less of athletic contests were carried out at that kind of a surface. You once visualized at a hockey game, I think, but go ahead, yeah.
That's right. So an ant walking on a crumpled sheet of paper would say, my God, the universe is complicated. There are all these forces everywhere.
Yeah.
Now, we looking at this sheet of paper knows that there's no such thing as force. The world is, in some sense, still flat. What is different is that space itself has curved. And that curvature of space gives you what we call force. This was Riemann's great idea 150 years ago.
He's back in the 1850s or so, right? Yeah.
That's right. That led Einstein to believe that perhaps space, maybe it's not crumpled so much, but is smoothly bent by the sun and by black holes. So Einstein replaced this crumpled sheet of paper with a bed sheet. Think of a bed, and think of putting a huge, gigantic rock right in the middle of the bed. And the bed, of course, comes into a depression.
Of course,
Then get a marble and shoot a marble around the bed.
Right.
The marble, of course, circulates around this large rock.
Right.
And you say to yourself, my God, that's gravity. That's force. There's a force exerted by the rock on the marble. Well, we know, of course, there's no force at all. It's just the smooth bending of space and time. So Riemann, Mach, and these people had the germ of the idea that perhaps it is the warping of space that gives us force. And of course, Einstein's great contribution was he finally wrote down the complete mathematics of that. That's one tradition, the tradition of the left brain. Now, nature has another brain, and that is the subatomic world of the atom. And in that world is the world of Max Planck, where we have little packets of energy whizzing back and forth. Quanta, little packets of discrete energy. And the quantum leap, in fact, is now part of our common conversation.
Yes.
Discrete, not continuous, jumps. That is antithetical to the smooth bed sheet of Einstein, that we now have these little packets of energy running around. And these two traditions could not be placed together. For 50 years, we physicists have been tearing our hair out trying to unify these two theories into a unified field theory of everything.
Yeah.
Now, you realize that many attempts have been tried.
Yeah.
All have failed. Niels Bohr, father of the atomic theory, once listened to a lecture by Wolfgang Pauli with his version of the unified field theory. Well, Niels Bohr stood up and he said, Mr. Pauli, we in the back are all agreed that your theory is crazy. But what divides us is whether your theory is crazy enough. Now we realize if you put this into 10-dimensional hyperspace, the quantum theory and the theory of Einstein merge like two pieces of a jigsaw puzzle. It's one of the most beautiful unifications possible. Two pieces of the jigsaw puzzle beautifully meshing together once you go into hyperspace. Now, how's that possible? If you go back to the carp swimming in a pond and it rains. Think of it raining one day and all these vibrations go on the surface of the pond. And now think that how the carp views these vibrations. The Karp would say there's a force. There's a force somewhere in this mysterious unseen dimension.
Force at a distance.
Force at a distance, right.
Right.
Well, today, we physicists believe that the unseen fourth dimension ripples. You cannot see it, but it ripples, and when it ripples, that's what we call light.
In what would be fifth or fourth dimension, what is traditionally called fourth dimension, or what might be called the fifth dimension.
If we had time.
Four spatial dimensions of space and one of time, right?
Right.
Yeah.
Right. And so the ripples of the fifth dimension, or the fourth spatial dimension, ripples can be seen, and that's basically what light is. Now, when I was in college, by the way, I was at Harvard, and I asked my professor at Harvard, what is light? And he said, light is a wave. Well, I said, if light is a wave, then how does it come from us from the vacuum of outer space? Nothing is waving. And he said, yes, in a vacuum, nothing is waving, but light is a wave.
We could say an absolute vacuum of outer space?
That's right. And I said, no, wait a minute, that's ridiculous. You're saying that nothing can wave. How's that possible?
Yes.
And he said, yes, nothing can wave. And I said, that's crazy. And he said, we just get used to it. That's all.
Right.
We've been used to the idea that nothing can wave. Now we believe that what is waving is the fifth dimension. Now, you may say to yourself, well, why stop at 5? Why not go to 6, 7? Well, when the 6th, 7th, 8th dimension starts to vibrate, then instead of getting the light force, we get the nuclear force. Now, this is profound. You realize that the nuclear force has stumped the world of physics for the last 50 years. What is the nuclear force?
Well, okay, now, and I wanted to back up again, because you're getting into like superstring theory and all of that we want to talk about, but coming back again there to this slower history, 19th century, 20th century, coming into that, we're coming into it to where they came to identify force, or they came to identify gravity, and then electromagnetic spectrum. And then the strong and the weak nuclear forces are 4 major forces, and these were things that were come upon, and were understood as basic elements or basic forces that are operative in terms of matter and energy. And maybe you could just even go step through that with us, because that's going back at basic primer stuff again. We have these 4 main things that have to be in a certain state rectified if we want to try and move toward this theory of everything.
That's right.
Now, how did we come to discover these things, and what was the path of that, and where did Ernst Mach play a role in all of that?
See, the Greeks, 2,000 years ago, thought that the world could be explained by 4 elements: air, water, earth, and fire.
Right, okay.
And then we began to realize that air is not really an element, that air consists of nitrogen, oxygen, and they in turn can be broken up into neutrons and protons. We began to realize that fire is not elemental. Fire is a chemical reaction.
We begin to realize this when? When do we begin to realize?
In the last 200 years.
200 years. Okay, we go back a little bit more, 200 years. Okay, you're right, okay.
So science really was at a standstill for about 2,000 years, since the time of the Greeks, till about 1700. Science was still extremely primitive, and it was Newton and it was the early chemists that began to slowly, painstakingly realize that the 4 elements are composite, that Earth is composed of many different elements, 100 elements compose the Earth, that the air has many different kinds of gases, and that
Linnaeus
fire
came with taxonomy.
And all this tremendously difficult coming out of the Dark Ages and the loss of all that Greek and Roman tradition. For 1,000 years,
and this knowledge began to build exponentially, as you say in your book. We began to get more and more. All right, go ahead, I'm sorry.
Starting with Newton. Newton began to, the first inkling that there was a force called gravity, an elemental force called gravity that made everything attract to the Earth, being attracted to the sun.
And
that was the first great force.
Dimensions, that's right. Cosmic implications.
The gravity makes the solar system hold together, it makes the galaxy hold together. It's the elemental force of the the That's the first force of gravity. Without gravity, by the way, we would be in outer space right now at 1,000 miles per hour without gravity. The second force...
Rather than just our television image going out there.
That's right.
It is now, in the electromagnetic sense. But go ahead, I'm sorry, please.
And the next force was electricity and magnetism. And the great Michael Faraday was the one who worked that out. In his laboratories, he had all these machines, dynamos and generators, and Disraeli, the Gladstone, the Prime Minister, once visited his office, and he knew nothing of science. And Gladstone sniffed and scoffed, and finally he said, Mr. Faraday, he said, your fame is widespread, but of what use are these machines for England?
The electromagnetic spectrum.
Electromagnetic
yeah,
waves, right. And so Faraday, thought for a moment, and he said, Mr. Prime Minister, in a very famous statement, he said, I know not what use these machines will have for England, but I do know one thing, and that is one day you will tax them.
And they certainly have. It's
Today,
about 50% of the gross national product of the planet, I think, now.
That's right. About 50% of the world's wealth is linked to television, radio, computers, cars, tractors, refrigerators. If you turn off electricity, we are literally thrown back to the time of Isaac Newton.
Right, and in a very real sense, gravity and Newton was the precursor, if that's the right term, to the Industrial Revolution itself that began us in terms of mechanical machinery and so forth.
That's
that there was a tie-in with this to the social economic development of the planet.
That's right. See, when I learned history in high school, we learned about kings and queens, and I knew that history was not in terms of kings and queens. Look at it in terms of force, that when Newton in the 1600s finally worked out the force of gravity, he also worked out what is called mechanics. Mechanics now gives us machines, and machines unleashed the Industrial Revolution, which toppled the kings and the queens of Europe.
Absolutely.
So in some sense, the unleashing of gravity and the theory of mechanics of Newton touched off a revolution that we call the machine age, industrial age revolution.
The Industrial Revolution began maybe 300, 400 years ago. Right?
That's right, and sparked off by Newton.
Right.
Then, of course, Faraday and Maxwell, tinkering in their laboratories and working with equations, set off the age of radio, set out the age of electricity.
Right.
All of a sudden, we had refrigerators and televisions and radios and vacuum cleaners.
Well, it took a time for that technology applied.
Right. But again, since the 1800s now, since the 1800s.
Right.
And then 50, 60 years ago, we began to unlock the secrets of the atom. All of a sudden, the third and fourth nuclear forces were discovered. And when we look at the detonation of an atomic bomb, that is perhaps the simplest unleashing of the nuclear force, which in turn, once again, changed all of world history. And then Cold War, everything changed with the discovery of the nuclear force.
It hasn't
each time.
Right. It hasn't
each time.
Yeah, it has in a very real sense. So, and it gives us these four main things in a certain sense. Gravity, we have electromagnetic spectrum, or electromagnetic, weak force and strong nuclear forces.
Right.
And these are four basic, what do we call them? Basic forces in universe by which we are concerned with in terms of that. When did we understand, what brought us to the point, if I'm correct in that these are four basic building blocks of the universe and moving toward a theory of everything? When did we come to, the scientific community come to understand that that was in fact things with which, and the reconciliation of the mathematics and physics of these forces is something that we have to deal with if we're trying to move toward a theory, ultimately toward a theory of everything? When did we come to understand that?
About World War II.
About World War II.
World
That's
War
just
II.
Yesterday, and I.
That's right. You realize that this realization, perhaps the greatest realization in modern science, is a recent one. That around World War II, see, before then, they thought it was just gravity, electromagnetics, and who knows what the nuclear force is, right?
So now we're back in the days of Ernst Mach and 1905 and those things that were going on at that time. We did not understand these things. We thought gravity and electromagnetism
were separate.
There were other binding forces or something that people tried to understand, but the knowledge was quite primitive in a certain sense until theory of relativity, or wasn't that around the turn of the century?
Yeah. See, what Einstein did was
I'm talking now at a theoretical level, in a certain sense, to where the knowledge base was beginning to emerge of what brings us to the modern era.
Right. You see, coming out of these two great traditions, the tradition of Einstein, looking at space and time, and that force is nothing but geometry, it was Ernst Mach, the great philosopher, who began to talk about these kinds of ideas, but he wasn't a mathematician. It took Einstein to put down the mathematics by which space and time can be bent.
Ernst Mach was not a mathematician.
He was a philosopher.
He was a
physicist and a philosopher, not
Austrian.
a mathematician.
Yeah, his daughter lives here, his granddaughter lives here in New York.
Oh, is that right?
Yeah, and she has an article for Parade magazine.
Is that right?
Right. Yeah, it's interesting.
That's the guy who inspired Einstein to think of...
Yeah, you had that in the book, that was the guide that Einstein followed.
That's right.
Ernst Mach.
That's right. That was the guide. Mach and Riemann had the idea of this crumpled sheet of paper
Yeah.
and that space was somehow essential to the understanding of force. But they didn't have the equations. Einstein was a master of equations,
Yeah.
and he was able to then put down the mathematics by which the bending of space can be represented as a force.
Yeah.
And then parallel to that,
Yes.
parallel to that development, we have the development of the atomic bomb. And the development of the atomic bomb gets us into the nuclear force, which was perpendicular and parallel, distant from what Einstein was trying to do. Now remember, at the Institute for Advanced Study, Einstein was considered a god, but an aging god, a
Yes.
god that no longer had great ideas anymore. All the action was in the area of nuclear physics.
Just by the young guys coming
The
up,
young hotshots,
They
the
tend
young
to do
Turks.
that. But a lot of stuff comes out of young people, doesn't mathematicians?
That's
It comes out
right.
of the youth often. But go ahead.
And
Yeah.
the young people said that Einstein's over the hill.
Yeah.
See, what
Well, they're
Einstein
always
wanted to
saying
do
that, right? Yeah.
was he wanted to unite these two great traditions,
Yes.
the tradition of Mach and Riemann, and the highest fruition being general relativity, which gives us black holes and big bangs,
Yes,
right,
right,
and
all
space warps.
Right.
And the other tradition, the tradition of Planck, the
Yeah.
tradition of atomic bombs and particles and quantum and atoms.
Going in quantitatively into the little parts of it. Is that what he called marble and wood?
That's right.
Yeah.
The world of Riemann and the world of Mach, Einstein thought was beautiful, was gorgeous.
Yeah.
The world of pure
Geometry.
space, geometry,
Yeah.
the world of marble.
Right.
And then Einstein hated this world of wood.
Yeah.
I mean, how many goddamn particles are there? There are thousands of particles.
Well,
Every
there
time
are
you smash an
subparticles,
atom,
yeah.
we discover
Quarks,
more
all
particles.
kinds,
Now they're
yeah.
quarks
Yeah,
or whatever,
yeah,
right?
yeah.
So Einstein said this is wood. This is wood, because wood, it comes in all sorts of varieties, and who knows what wood is, right? So Einstein had these two great traditions of marble and wood, and he
Yeah.
said that a unified field theory
Yeah.
must be a theory where everything is made out of marble. The wood must turn to marble. And he spent the last 30 years of his life at the Institute thinking about how space could be used to describe matter. His idea was that we are nothing but condensations of space, that space somehow condenses, like a cloud condenses out of nothing, right? All of a sudden, on a hot day, a cloud condenses and rains all of a sudden, right? Einstein thought that maybe space condenses, and instead of a cloud, we get people. Maybe we are nothing but condensations of space. Now, the irony is that even though the Young Turks, the creators of the quantum theory, scoffed at Einstein and said that what God has torn asunder, let no man put together. That God had meant these two traditions to be separate. Marble shall not be wood. Geometry shall not be quarks.
Is it fair to put one in the term of a holistic or comprehensive view, and the other into a more quantified or specialized kind of approach?
That's
to things?
right.
Is it fair to put those two things
Exactly.
as being a holistic approach as opposed to a quantitative break-it-all-down approach?
Right.
That has been a consistent theme in science and well, even in just intellectual history in general.
Right. There are two great traditions in philosophy. One
Yeah.
is called reductionism or mechanism. That is, you get a clock, and you say to yourself, what is a clock? Well, let's get a hammer.
Yeah.
And you just smash the dickens out of that clock, and you look at the pieces, and you try to put it together. Or take an anthill. You want to analyze ant behavior. So what do? You smash the atoms apart of the ants, and you take the DNA, and you try to figure out what makes ant behavior tick.
Now,
aren't
you, if I may, Michio, aren't you revealing a little bit of your own prejudice by taking such a view of smashing things apart?
But that's
they're
what
going to do it a
we're
little bit more carefully than that, and they're going to do it more
That's what we do.
precisely and with greater precision.
We
and
smash
Max Planck,
atoms.
And in the quantum tradition, quantum mechanics, there was a great deal of careful, disciplined thought, and a great deal. They weren't just smashing, but they were
We
smashing
smash atoms.
right?
Look, when I was in high school, by the way, as a footnote, I built my own atom smasher.
I know.
Okay?
I know you blew.
I know
every
all
fuse-
about atom
fuse
smashers.
in the house. Right?
That's right.
Yeah.
I got 300 pounds of transformer steel. I
Yes.
asked my mom permission to build an atom smasher in the garage, and she
Yeah.
said, "Oh, yes, sure, go ahead." Right?
Yeah.
It was 6 kilowatts, 300 pounds, 22 miles of copper wire, and whenever I plugged it in, I would blow out every single circuit breaker in the house. All the lights would go
Your
out.
poor mother.
And my
she
mom,
should have just had a kid that would go sledding and stuff, But anyway, go ahead. Yeah.
she said, "Why
Yeah.
can't you play baseball?"
Thank
I mean, she bought me a basketball once.
Yes,
She said, "Hey,
right.
here's a basketball.
Yeah, right,
Why do you
right.
build these machines?"
You're building a particle accelerator. or
Right.
something,
So I tell that tradition is very deeply ingrained in us quantum physicists. I'm a quantum physicist.
You are a quantum physicist.
That's right. And we smash atoms.
Okay, you're a quantum physicist.
That's
All
right.
right. All right, go ahead.
And that's the second tradition.
Yeah.
The tradition of Einstein is the smooth world of marble.
Now, what do we call them?
We call them relativists.
Relativists,
And geometers.
right?
And
Yeah.
geometers.
Okay.
I'm a quantum physicist. We believe in smashing atoms. That is the reductionist approach.
All right.
Now, the irony
You're a
is...
reductionist?
I'm a reductionist.
But you're a holistic, you have a holistic
But
view of
ultimately,
superstring. We're gonna
ultimately,
get
in the
to a
last
holistic
10
view,
years,
yeah.
right? In the last 10
You're
years...
a reformed? Are you a reformed something?
I'm a reformed...
Do they have a 12-step program for reductionist quantum mechanics?
In the Reformed
physicists?
Church of holism, right?
Right. No, but go ahead. I'm sorry.
Okay, so I started off as a reductionist. I started off smashing atoms since high school.
Yes.
Edward Teller was my mentor. Edward
Yeah.
Teller got a scholarship for me to go to
Got
Harvard.
you to Harvard, yeah.
That's right, and I basically was smashing atoms all my life.
Yeah.
In the last 10 years has been a dead end for that branch of physics. We've smashed all the atoms we can, and we find very little to explain why we have the world that we have today. Why do we have so many thousands of particles? You know, Oppenheimer, who discovered the atomic bomb, once made the statement that we should give the Nobel Prize in physics to the physicist who does not discover a particle that year. Because there's so many of them. And Enrico Fermi says, why do we give them Greek names? If I wanted to be, if I could memorize these Greek names of particles, I would become a botanist, not a physicist.
Yeah.
Right?
Yeah.
Today, we believe that the two traditions, the tradition of marble and wood, can ultimately be merged together in hyperspace.
Do people from both sides of the sphere think that way?
The leading physicists believe this. Okay, now remember, this is a very difficult theory to test. This is a theory of creation. It's the theory of the ultimate nature of reality.
I understand. That's why we're going step by step. We're getting at the theory of everything in a certain sense. But I mean, had the Einstein, what do you call them, the relativists?
Relativists.
You said the quantum mechanics reached a certain point a few years ago. Had the relativists reached a certain point at the time the quantum mechanics came out? Had they reached a certain dead end in terms of as far as they could go?
Exactly.
Were the limitations the mathematics? Were they the limitations of the knowledge base? Or what was the limitation that they ran into as far as developing toward this unified field theory that Einstein was seeking? What had they run into? What had been the problem?
I think you hit the nail on the head.
That allowed quantum mechanics to come in with such force in, what, the 30s? Or?
Well, quantum mechanics came in the 30s. But you hit the nail on the head. You see, the two great traditions, the tradition of marble, of Mach and Riemann and Einstein, hit a dead end. The tradition of the quantum physics hit a dead end. And they hit a dead end, okay, in the following way. The geometers gave us the Big Bang Theory. That is, at the 20 billion years ago, there was a cosmic explosion. But they couldn't explain what happened before the cosmic explosion. They couldn't explain where it came from. Or take a black hole, which we've actually discovered now in outer space. It was announced in 1994, before the summer, that M87, a galaxy that is 50 million light years away, is a swirling gas containing perhaps billions of solar masses, and in the very center is a black hole.
This is the one of which you had a photograph, or NASA put out a thing?
That's right. NASA has a beautiful color.
See that. Yeah, right.
Yeah, beautiful color rendition of M87, a swirling gas of hydrogen coming into the center and then shooting off radiation into the North Pole and the South Pole, looking like a cosmic top.
Yeah.
At the very center is the black hole.
This is the black hole.
Now, this is where gravity began to break down.
Yes.
Because at the very center of the black hole, if you take a look at Einstein's equation and look at them continuously, at the very center of the black hole is a looking glass to another universe. There is a parallel universe, a wormhole, that takes you through the black hole into another sector of space and time.
Another universe.
Another universe. Now, people began to say, holy mackerel, this is
indeed.
heavy nonsense you're talking about, Einstein's theory. And yes, let's go back to the sheet of paper. When we were in elementary school, our teachers told us the shortest distance between 2 points was a straight line.
Yes.
In fact, you didn't pass
Shortest
fourth
distance.
grade until you said to the teacher that a straight line is the shortest distance between 2 points. That's wrong.
That's wrong?
That's wrong.
Dear me. All right, go ahead.
The shortest distance between 2 points is a wormhole. You take the sheet of paper, you bend it, and you bring these 2 points together, and you hop across by punching a hole in space. It is a wormhole that is the shortest distance between 2 points.
And these universes can be connected by these wormholes.
That's right.
They could be. This is all theoretical.
It's all theoretical, and this is where Einstein's general relativity began to break down.
I want to bring in something that can be just put maybe completely off to the side and not have anything to do with what we're talking about. But does this have anything to do with fractal geometry or not? Or not? Maybe we don't need to go into that at all.
Ultimately, at the quantum level, but not directly. Not directly.
Not
I'll
directly.
explain maybe a little bit later where fractals
Mandelbrot
can.
and that stuff.
Yeah, I'll explain later where that does come in. It at the quantum level.
Okay, go ahead.
Okay.
Yeah,
But you see, at this point, the relativists, these pure geometers, began to realize that they were running out of gas. They could not explain the instant of the Big Bang. They could not explain the center of the black hole, where Einstein's theories actually say that there is a looking glass that if you go through the ring of fire, the black hole is a ring, you go through the ring, you wind up in another universe.
This is Einstein.
This is Einstein's theory,
Yeah.
right? Okay.
Okay.
Now, that's where people began to say we have to go to a higher theory. A
higher dimension.
A higher dimension, right?
Yeah.
And at this point, we have now the victory of holism over reductionism. Reductionists said we have to smash the atoms, get to the quarks, but what's inside the quarks?
Yeah.
We now think that what's inside a quark is a vibrating string.
All right, yeah.
They're infinitely tiny vibrating strings.
Now we got these two traditions, and we've got this, and the black hole, and the loss of the gravity, and it's the gathering of that, and that through that would be where the parallel universes in another dimension, and that they are connected by wormholes that are called. Why wormholes? Why wormholes?
Because if you think of the Earth and you think of a worm burrows a hole in this direction and comes out here. So you could say that the shortest between 2 points is to walk across. Or you could simply burrow your way through.
Like a worm.
Like a worm.
Could
and
be
take a
snake
shortcut. A snake hole, right?
Yeah.
Think of an apple.
Yeah.
You could go across the apple the long way, or the short way is to just burrow right through the apple, like a worm does. Okay? And that's called a wormhole.
And in order to do that, you'd have to have another universe to which one is going.
That's right.
And most people are of the mind that we live in this universe that we understand from Big Bang. I thought it was 15, you say 20 billion years ago we have this understanding, all of which comes to be accepted common knowledge, as it were, among the physics and the broader intellectual, or the community. We understand this Big Bang, and that was the beginning of our universe as we understand it, but that there are universes beyond the universe that we understand.
That's right, parallel universes.
Now,
okay, now remember,
has this been common knowledge among physicists and theoretical physicists for a long time, and if not, how long? And when did this come up? This idea of parallel universes and the wormhole and that sort of thing. And Mr. Hawkins talks of this.
Hawkins talks about this. That's right.
Physicist,
right.
But maybe you could fit in there, and we'll go along that line. If you could.
So see, 10 years ago, these two great traditions, the tradition of Marble, of Mach, Riemann, Einstein, curved spaces, came to a halt when they had to deal with what happened before the Big Bang. The other great tradition, the tradition of atoms and quarks and molecules, that also came to a halt because we realized that we didn't understand why there were so many thousands of particles and why you couldn't write a quantum theory of gravity. Why couldn't you write a theory of all forces?
Because in the quantum theory, they could get accommodation of these mathematical, if I may, mathematical formulations or these things. A lot of this is mathematics, of course, but that they could not accommodate, as it were, gravity.
That's right.
In terms of quantum mechanics theorized.
That's right.
And that was the thing that couldn't be brought in. Edward Whitkin or something said that in superstring it does, if I understand right.
Right. So 10 years ago, there was a revolution. 10 years ago, we realized...
That was the hang-up with quantum theory? They couldn't accommodate...
Gravity.
If that's the right term, accommodate gravity in terms of its theorizing, right?
That's right.
Okay, and that was their hang-up 10 years ago.
Right.
All right. Go ahead.
So in other words, in some sense, Einstein is having the last laugh. We recall that
at
people
this moment in 1994?
Yeah, up there.
Yeah, right.
Up there in space, right?
Hyperspace.
In hyperspace, right?
Yeah,
He's having the last laugh. He's saying, I told you so. I told you so.
He was a smart son of a...
40 years ago, he was talking about unification.
Yeah.
He was talking about harmony,
Well,
holism.
wasn't Max Planck ever talking about unification? Weren't the people on the other side talking about unification? Weren't the atom smashers talking about unification?
No. They wanted to smash those atoms. They wanted to get smaller and smaller particles, hoping to find some kind of simplicity among the billions of particles they were discovering.
Yeah.
And instead, they were getting deeper and deeper mired in the mathematics and the flood, the tidal wave of particles coming out of our atom smashers.
Haven't we discovered a great deal by, I mean, if we were to look at academia and we look at the breaking up in knowledge, I mean, there's a seamless web and an understanding, and in a certain sense, you've got the ultimate theory of everything. But the academic process, the whole process of learning, the whole process of understanding the whole adventure of universe and the biological system, the whole academic process, learning process, is one now of tremendous specialization. We have specialization upon specialization upon specialization.
Right.
And hasn't that been the source of a considerable amount of progress? And hasn't there been a considerable amount of progress toward increased understanding? I don't know if the analogy is right between, you know, the theory of everything or a unified field theory as a comprehensive view of the universe, but the specialization and the breaking down of everything into its component parts. It's reflected in our societal organization and so forth.
Well, yes and
Isn't
no.
there something good to be said for that?
Well, you see, some people think of medicine as being so specialized that we don't talk to each other in the field of medicine. However, there is also a unification process taking place in medicine with the discovery of DNA.
Right.
DNA is a string.
Right.
A string that incorporates a fabulous amount of information on it. 3 billion base pairs, 100,000 genes, all compactified into a string.
Right.
So that all biology now revolves around the master chemical, which is DNA. Right. So out of all these specializations in biology came a unification called the string, DNA.
Well, I
in
understand
physics,
that. Yeah.
we have a similar thing happening. In physics, we had people who specialized in gravity, people who specialized in electromagnetics,
and
people who specialized in the nuclear force.
I know.
Now,
right.
after all these specializations, we realize that we're talking about the same object.
Well, I'm still
a string.
And I'm still saying, in terms of the way the society organizes, the basic premise is that specialization is the way to go. And if you become specialized, and they become specialized in little disciplines all the time, and the more specialized they are, the more you are. And if you are not specialized, you in the scientific community, you have the danger of becoming called a popularizer, or someone who is a generalist, a jack of all trades, master of none, doesn't know what he's talking about, because we specialists know all the nuances of what's going on in this specialized field, and that's something that is current now in academic structure, academic development, and intellectual history, and social organization.
Well,
it may be the major problem that's facing mankind is we don't have comprehensive vision. There was a piece in the New York Times, Sunday Times this week, saying that science, they're now trying to come to a science of science, or some sort of an epistemology that takes into them all and brings them all together. But specialization is the order of the day now.
Yes and no. You see, specialization is only the tip of the iceberg.
All right.
Specialization is when you look at an elephant and you say, I'm going to specialize in the ear. I'm going to specialize in the foot. I'm going to specialize in the trunk. I'm going to specialize in the tail.
Right.
Until you look at, all of a sudden, the big picture and you realize, holy mackerel.
Yeah.
We specialize to the point that we miss the forest for the trees, that there's a unification taking place, that evolution has created a spectacular animal called the elephant.
Yeah.
The same thing now in physics.
Yeah.
That some people specialize in the trunk called light. Some people specialized in the foot called the nuclear force. Some people specialize in the tail called the weak nuclear force. And all of a sudden, looking at it from a distance, we say to ourselves, oh my God. All these specializations going deeper and deeper into the structure of matter have given us a unification. We see now the big picture. Just like DNA has unified most of the life sciences, the superstring that is inside the quark, there is even a tinier vibrating string, like a violin string, is the unifying principle that allows us to unify the specializations. You know, when I was a graduate student at Berkeley in the late 1960s and 70s, you had to specialize. My thesis advisor came up to me and said, you got to specialize.
Well,
you got to work in general relativity, gravity. You got to work in electrodynamics. You got to work in the weak force. You got to work in the strong force. What's your specialization going to be?
Yeah, right. And that was the pathway towards acceptance, and still is in the society.
20 years ago in physics, that was the way it is.
In the society, you look in the society, they don't have room for comprehensivists.
But you see, the deepest, most profound,
geopolitically or economically or politically, or even if we take an analogy of nationalism and supranationalism. They don't have a sense of ecological inclusion in terms of decision-making and so forth. Specialization is still the course that is mapped out for our young minds to follow, and it's a way of, I mean, there is no discipline of everything.
But there is. You see, what happens is as people begin to specialize, the discipline itself forces you to come to a deeper, more profound, unified reality. Physics has forced all these graduate students working in 4 different areas to unite in a common theory of everything. In biology, We have all these people specializing in plants and animals and humans and whatever, forced to come to grips with the unifying principle of DNA.
Then you have the social sciences, and then you have the arts and the humanities, and the purpose, you know, and the biological, the virology, the link between the living and the animate and the inanimate, and how they all fit together.
Right.
And the thing is that your superstring theory and this thing is bringing us to an understanding of a theory of everything, that there is a seamless web of unity among all things.
Right. And this is why I say that Einstein's having the last laugh. Because Einstein saw the process of specialization. He saw the people at the Institute laughing at him, saying that, oh, gravity is old hat. The new sexy stuff is atoms and neutrons and protons, and that's where I want to specialize. And Einstein revolted against that. He didn't like the fact that all these physicists were specializing into little pieces of physics and drilling holes wherever they could. He once said that he has no respect for a physicist who takes the thinnest piece of wood and drills lots of holes in the thinnest piece of wood and says, look, I've made a scientific accomplishment. Einstein wanted to take the thickest piece of wood and drill one clean hole through it, not to take the thinnest piece of wood and drill lots of. The specialization process taking place. The last laugh is, ultimately, when you go to a deeper reality, unification steps in. That the discipline itself forces you, kicking and screaming, the discipline itself forces you to begin to have a comprehensive theory of everything.
Okay, because if you're talking about a theory of everything, I said earlier, the science of science, you know, or epistemology of or understanding how we know what we know, but that there is a unity coming, a Taoist, I mean, we begin to get at some sort of an understanding of this being some sort of a qualitative transformation in the
paradigm shift.
A paradigm shift on a very large scale.
That's right.
I mean, because we can begin and say 15 to 20 billion years ago, Big Bang. Then there was the development of this, and I don't know, there was when did life begin? I
About
guess
3 billion years ago.
3.5 billion years ago.
Right.
Plants started 3-4 billion years ago. There was this development. I don't know if the DNA, mitochondrial DNA research is correct. 200,000 years ago, Homo sapiens sapien appeared in Africa. We migrate out. We go 200,000 years. We get up. 200 years ago, we didn't know what the heck we were talking about.
That's right.
Before
Newton,
this exponential, and all of the curves, now as you and I sit and talk in, what is the month? July, 1994, all of the curves are going exponential now.
Right.
They're going.
Right.
So that we're coming into some sort of a new relationship to universe other than that to which we have been throughout the whole of the human experience.
Right.
You feel this.
Right. Some people look at all this information.
I mean, that gets a little bit, yeah, okay, go ahead, I'm sorry.
And some people feel like overwhelmed. And I used to feel overwhelmed when I was a graduate student getting my Ph.D. in 1972, just overwhelmed by all this knowledge coming at us. But I tell you, being a physicist today is so much simpler than being a physicist when I was a graduate student. It's simpler because we realize that in hyperspace, in higher dimensions, up to 10 dimensions, we have all of a sudden a simplification of all the forces of nature. I like to look at the analogy of an Egyptian 3,000 years ago looking at the weather.
Yeah.
Some people would specialize in clouds. Some people would specialize in why it got hotter as you went south. Why do the winds blow from the west? Why does it rain? Why do we have summer, fall, winter, spring?
It'll blow from the west depending on what latitude you're at.
That's right. But the Egyptians the weather was a complete mess. Everyone specialized in different aspects of the weather. Now take an Egyptian into outer space. Take some of the primitive ancients and send them into outer space where they could see the Earth from the third dimension. From the third dimension, they see the Earth tilted to 23 degrees. That's why we
23.5 degrees, the plane is ecliptic.
Right. That's why we have summer, fall, winter, spring. They can see the Earth, the equator. That's why it gets hotter as you go toward the equator. They can see that the Earth spins counterclockwise, which means the winds blow in a certain direction.
From the North Pole.
From the North Pole.
As viewed from the North Pole.
That's right.
Yeah.
So looking at the third dimension, all these specializations simplify and unify by looking at the third dimension. That's why hyperspace. In mathematics, they always say, you must leap out of flatland.
Yeah.
When you leap out of flatland, then you look down at flatland, you see all these little specializations everywhere, begin to realize, my God, it's simple. It's so simple when you have a unifying principle. And one of the great unifying principles of mathematics and physics is to leap out of flatland.
We had
jump into space.
We were talking about that, Mark, and so we didn't talk about this incredible Flatland, which had such an incredible book where they had all the figures were drawn in flat, you know, one, two dimension. You put a circle around a stick figure and he's in jail.
He's in jail, right?
And it was Einstein. You have a picture of Einstein lifting him out into the other dimension, into the fourth dimension, or into another, or third dimension in that case. If that were the case, that would be the possibility, and particularly since we're being flooded with this information, and we were talking earlier on camera, you have in cybernetic language, they have a discussion that information or systems analysis, if you have an information overload within a system, or what Bucky Fuller would have called special case experience, that you have information overload permits pattern recognition between a system that would be overwhelmed here, but you can see pattern recognition between various other parts of the overall system that might mean that we can draw away from this whole system and begin to see it whole in a way that we've not been privileged to do historically. And this might be the shift that we're going through.
And in fact,
now,
theologians have stated that if we go out of the tabletop and into the third dimension and look down, we can see everything. A pattern recognition of all different sets. And this is why some theologians have said that God and spirits and ghosts live in the fourth dimension. Think of it for a moment. If I have people living on a tabletop, flatlanders, right?
Flatlanders,
I can get a scalpel and cut right into their insides without cutting their skin. Without cutting their skin, I could perform surgery on their inside. Or I could peel them off, in which case they simply just disappear off flatland. Or if they have a safe with gold in it, I can simply reach in the safe and just pull out the gold.
And it's gone into nowhere.
It has gone into nowhere, right. Now, Picasso was fascinated by this four-dimensional perspective, that you could look at a flatlander and see all of flatland at once.
Well, then came Cubism.
And then became Cubism.
Right.
So look at the development of art. In the medieval ages, art was flat and two-dimensional.
Didn't even have perspective.
No perspective. You know, two-dimensional art, everyone is flat. Everyone looks like this in these medieval tapestries. And that's because God was omnipotent. And if God is omnipotent, there's no eye. God can see everywhere simultaneously. And that's why medieval art is flat. Now, Da Vinci, on the other hand, looked at everything from the perspective of the eye. That means lines of perspective shooting out from the eye. And in the Last Supper, for example, you can see the lines coming out at you at Jesus Christ looking at the scene of the Last Supper. So Renaissance art discovered the third dimension. And what Picasso said was that if medieval art was two-dimensional, and if Da Vinci Now, you go to the Museum of Modern Art, and you see all these people gawking at Picasso's work, and you listen to their whispers, and you hear them saying, my God, why couldn't he draw? Why does he have to have a woman's silhouette with two eyes facing forward? But you see, they don't realize that Picasso was trying to capture the fourth dimension. That just because we can see flatland all at once, this means that a four-dimensional person looking at us can see our two eyes, our silhouette, side and back, simultaneously.
And that became part of that. Well, then if you have that in systems analysis, it's also possible that if you have this, that you have this, you can see pattern recognition between subsets or special case parts of a system. That could be an organism, or it could be cells and organisms, organs, an organism. You could see it whole. But then he also had this concept of synergy, saying that there is a behavior of systems that's unpredicted by the sum of its parts. That there is a resonancy that interaccommodates systems that is unpredicted by the sum of its parts. You might take the analogy of the birth of a baby in an embryonic state within the mother's womb is going to be coming into a new relationship to a universe that, or to a world that can't be known from the context within the system itself. It's from above that it can be seen in a certain sense in a new and different kind of way. So that could be something that could be a little bit disquieting to people who are in a system that is comfortable. It would be uncomfortable to a flatlander to consider three-dimensional. It would be uncomfortable for most human beings, as we sit and talk July 1994, to consider a qualitative transformation in the theory of everything, which could lead to and would have social, political, economic, and other ramifications as well upon the operation of this interrelated system, spaceship Earth, within this solar system, within this galaxy, within this hyperspace world. It's a rather large kind of transformation. It'd be a little bit difficult for a lot of people to grasp, and yet that is exactly what, in a certain sense, your book is asking us and laymen to understand is the appropriate way for us to begin to think.
Right. And speaking of synergy, right,
Yeah.
the sum being greater than the sum of its parts, take a look at a jigsaw puzzle. If we have the jigsaw puzzle, the different pieces make no sense. But when we put them together, all the jigsaw pieces all of a sudden make a picture.
Yes.
And we suddenly say, oh my God, a picture just jumped out at us.
Yeah, that's
the
right.
same thing. These jigsaw pieces are the forces of nature.
Right.
One jigsaw puzzle piece is gravity. Another one is light. Another one is the weak nuclear force. The other one is a strong nuclear force. And when you put them all together into a picture, all of a sudden something new jumps out at us, and that is the 10th dimension. That is in hyperspace, in a out-of-flatland perspective, looking down at two dimensions. We suddenly see that all the forces of nature are simple, whole, and extremely easy to understand.
That's another one of your principal observations of the book, is at another level, things become simple and elegant at another level of a dimension, at another level. They become simple and understandable.
That's right.
And in a certain sense, it might be this kind of vision of this kind of transformation that there's so much dis-ease among the world citizenry. As we begin to look at the real world, we want to do that in a follow-up talk with you about, we want to go into superstring. We've hardly touched on it. You've been trying to get at it, I understand. But then we're going to this kind of a situation. That's what people are, in a very real sense, perhaps looking for now. It makes this, is there a Chinese expression? Let me not live in exciting times or something, but we live in a time of unparalleled qualitative transformation in terms of the evolution of events in this part of universe, and the understanding of that is what, perhaps in a very real sense, to go against the second law of thermodynamics, is to move across entropy and bring increased patterns of understanding to the process of which we're a part. We may be reaching a new moment in that period as we sit and talk now. But one thing we have even in television, and this signal as it goes out into the universe, is we run out of time within the context.
We barely scratched the surface of
and this is just the
hyperspace.
first part. We'll come back. We'll come back to a second part. But Michio, thank you very, very much. We remind you, the audience, we're talking with Michio Kaku about his book, Hyperspace. We've only just begun to talk, and we want to begin to get at some of the real interesting implications of superstring theory, which he's a leading proponent, and to get at some of the social implications of that. So we invite you to tune in. There'll be a second part coming up following next week. So, Michio, thank you very much for this part. And we here, I invite you to stay tuned. We'll be coming back again with the second part. Thank you very much for viewing this, and we'll see you next time. Again, Michio, thank you very, very much. And
It's been my pleasure.
we'll continue in a moment. Stay tuned. We're coming back next time.